Alright, starting with chapter 7.3 and chapter 7.4. They kind of merge together, and 7.3 is not that long, so we're going to put them all into one big happy family. Alright, remember last year we talked about the Bohr model and how it was great for looking at quantized energy, but not very accurate in terms of what an atom actually looked like. That was actually more like the Schrodinger's than it was the Bohr. So we're going to look at the Bohr for the quantized effect, and what that basically means is if I have hydrogen, I have one electron right there, and he can jump to the second energy level if I heat him up or I shine light on him or anything like that, and then he'll go back down as soon as he can. Or he might jump up if he has enough energy to the third and go back down to the second or to the first. Or he might jump up to the fourth, so on and so forth. Okay, we redrew this with the first energy level being 1, 2, 3, 4, and notice every time it cuts about in half. 5, 6, and that one's not really half, but it's kind of hard to, okay, 7. And we can say our electron can jump, and then it can fall back down. Or it can jump, and it can fall back down, or it can fall just down to the second one. And it can jump, and it can fall, or it can fall, or it can fall. Anytime that it falls back to n equals 2 is when we see it. Okay, the energy that it is giving off is the energy that our eyes can detect. And so we'll see some color associated with it. That's why the fire burned red, or the fire burned purple, or white, or whatever color it was burning at the time. We can use the equations that we've already looked at, E equals hc over lambda, to calculate what that energy is from the color that we saw. Well, if instead we know the two energies, we know the energy of n equals 3 and we know the energy of n equals 2, then we can calculate what we should see, right? And it has to be able to go both ways for it to be accurate, right? Just because you say that you know something because of one thing, you should be able to prove it in reverse. And so let's calculate the equation that Bohr came up with to discuss this was that the energy level should be equal to 2.178 times 10 to the negative 18 joules times Z squared over N squared. Well, Z squared is talking about the effective nuclear charge. Or how many protons I have. Right? So if I have 2 protons, I have a charge of 2 plus. If I have 4, I have 4 plus. Okay, and then we're going to square that. The n is the quantum level that we want to look at. So going back here, N1, N2, N3, N4, right? Not moles in this case. So yes, they use this more than once. Don't get that confused. In this case, it is the n equals 1, n equals 2, n equals 3, not the number of moles. So let's look at this, and since we can't see the first level of hydrogen, let's calculate what the first energy level, the difference between the first energy level and second energy level of hydrogen is. All right, so the energy level for the first level of hydrogen should be negative 178 e to the negative 18. Z squared for hydrogen is 1 squared, right? Hydrogen has 1 proton divided by the first energy level is what we're looking for. So that would be just this number. And we'll get our second bell here in just a second. So negative 2178 e negative 18 joules. the second energy level then should be and my effective nuclear charge, my Z, is still 1 for hydrogen, but this time I'm going to see what the second energy level looks like. So it would be 2 squared, so it's going to be 1/4 of that number, so negative 5.44 e to the negative 19 joules. And now, just like we did last year, we subtract the two levels. And that will give me a number of 1.633 e to the negative 18 joules. Okay, rearranging the formula that we had from last year, energy is equal to H, there's the other one, C over lambda, so that I can find out what the wavelength I need. Wavelength is equal to hc over energy, 6.626 e to the negative 34 times the speed of light, and I'm going to do this sideways here, 2.9979 e to the 8th. Isn't that beautiful? And then the energy that I just calculated, 1.633 e to the negative 18 joules, will give me 121 nanometers. Okay, so that is not within our realm of seeing. That's too much energy for us to see, but we can calculate these levels using this formula.